In 5.3, we're going to be talking about linear function patterns and what linear functions are. So our learning goal is I will write linear functions from graphs or tables. I will solve linear functions and I will solve real-life problems. Oops. Okay, something you're going to notice about 5.3 in linear functions is it's pretty much exactly what we did with linear equations before. We're just going to be using slightly different language to describe these. Basically, a linear function, it's any function where the graph is a non-vertical line. So remember, a vertical line would be a straight up and down line. That's not a function because for one input we'd have infinitely many outputs. But any other line is going to be considered a linear function. So all of our linear equations, except for the ones that started with x equals, like x equals 2, x equals 5, x equals a constant, every other linear equation that we did could also be considered a linear function. So this really isn't anything different than what we've done before. To write our linear functions, we're looking at our linear equations, and that's basically what we're writing down. Okay, so for our first example, we're given a graph. Hopefully you can see the points on that graph. And we're asked to use the graph to write a linear function that relates y to x. All this is asking you to do is to come up with the equation, or the relationship between our input, which is x, and our output, which is y. So to have a linear function, we need a slope, and we need a y-intercept. And that will give us a relationship between our y values and our x values. So to find our slope, I'm going down 1, 2, 3 over 1. So slope is negative 3 over 1, or negative 3. That's our change in y over our change in x. Our y-intercept, I intersect the y-axis at 1. So our y-intercept is 1. So our linear function that relates y to x will be y equals negative 3x plus 1. And that's all we have to do for using our graph to come up with the linear function. For example 2, we're asked to use the table to write a linear function that relates y to x. So again, we need a slope and we need a y-intercept. Remember, our slope is our change in y over our change in x. And if we're talking about a linear function, that does need to be a constant change. We can't change by 2 here and 1 here, and then change by 7 here and 1 here. It needs to be a constant relationship. So let's look at our change in y. It looks like I'm going down 2, down 2, down 2. Our change in x is up 1, up 1, up 1. So our change is negative 2 over 1. Negative 2 over 1, negative 2 over 1. It's constant. So our slope is going to be negative 2. Now for our y-intercept, remember that is where x equals 0. So at 0, y equals 3. I could also find that by using, point-slope form or slope-intercept form and plugging in one of my points, by graphing and seeing where I cross the y-axis. I could do any of the methods that I did in an earlier chapter to find this y-intercept. But now that I have it, my linear function is just y equals negative 2x plus 3. So for example 3, I'm given a real-life situation with data in a table that I need to graph. I need to determine if it's continuous or discrete. I need to write a linear function that relates my y values to my x values, and then I need to answer this question. So what we're looking at here is we have a table of hours jogging versus how many calories burned. So if you jog for 2 hours, you burn 800 calories. 4 hours burns 1600. 6 hours burns 2,400. 8 hours, that's a lot of jogging. Maybe it's in a week. 8 hours of jogging burns 3,200 calories. So the first step says to graph the data in the table. So I already have an axis here. I'm going to graph 2 800. You can just barely see that, but there's 2 800. There's 4 1,600. 6 is 2,400. And 8 is 3,200. So I graphed those amounts. And the next question asks if the domain is continuous or discrete. So we need to ask ourselves, are those the only possible hours that you could spend jogging? Could I jog for an hour? Could I jog for half of an hour? Could I jog for 4.25 hours? The answer to all of those questions is yes. I could do fractional amounts. There are amounts in between that I could jog for. So therefore, this is going to be a continuous situation, which means I actually want to connect these points together because it's continuous. And when I do that, you can see if I jog for 1 hour, I'm going to burn 400 calories, which just looking at the chart, that's pretty obvious to see. So our next step is to write a linear function that relates y to x. So you can see I have a straight line here. My y is changing by 800 each time. My x is changing by 2 each time. So my slope is going to be 800 calories per 2 hours, or 400 calories an hour. So that's going to be the slope for my linear function. And then my y-intercept is actually easy to think about in this situation. If I don't jog, I don't burn any calories at all. So my y-intercept is going to be 0. So therefore, my relationship, or my linear function that relates the two, is going to be y equals 400x. So there's the linear function. And then finally it says how many calories do you burn in 2.5 hours? I could try to answer that by looking at this. And I can see it's about 1,000. That's not too hard to do in my head. But in order to figure it out officially, I could put in 2.5 for x, because x is the number of hours, and I'll get y equals 1,000 calories for the answer to that last one. So the real life situation really wasn't any more difficult than the situation that was just random numbers.